So the lecture today is going to be linear vector subspaces. So it's basically like linear algebra. And oops. Okay. So, and you know, as always, please feel free to unmute yourself and ask questions. So what is a, okay, maybe I have to say at the beginning that for the purpose of this talk, so I'm going to assume that my field is just a complex number, or, you know, what we saw before by fundamental theorem of algebra. So I'm going to assume that this is the constant, you know, coefficient. So I have complex numbers, and either I take the kind of trivial valuation that every element in my field is going to be mapped to 0, or I'm going to, when it's needed, so I'm going to take the Puiseux series and look at the series, you know, like CT, and then for every coefficient, which is like a series, like, you know, with terms like in T, I'm going to take the minimum exponents, like as my coefficient. Okay, so let's start by reviewing basic linear algebra definitions. So if I have, you know, if I have a d-dimensional linear vector subspace, like in an n-dimensional space Kn, so there are different ways to kind of present this d-dimensional vector space, right? So like the easiest way perhaps would be, you know, taking d different vectors like in Kn and saying that this linear space is the span of these d vectors, like let's say v1 to vd. And another way actually to represent so this vector subspace, which is like equivalent by taking these d vectors, is that, you know, you just put these d vectors as the columns of your matrix, and then you say your vector space is the row space of this d times n matrix, right? And you know, another way, so like a second way to see like this linear vector space is by taking, you know, bunch of linear equations and defining it as the solution space of this linear equation. So if I have a d-dimensional space like in Kn, so I would need n minus d linear equations to minimally generate the solution space. And there is a third way that we're going to focus more like during this talk, and it's going to be in terms of Plūcker coordinates and Plūcker vectors that I'm going to explain further, you know, what do I mean by these Plūcker coordinates. Okay, so what is the goal of this talk? So we are going to start by, you know, taking a d-dimensional linear vector subspace L, and mainly we are interested to describe the tropicalization of the corresponding variety. Right? Whenever I had, for example, here, if I take the, you know, presentation of my vector subspace as a solution of n minus d linear equations, so that means to compute the tropicalization. So I have to take like all these polynomials, tropicalize them, right? And then look at the solution of every tropical polynomial, and then that would be my tropical variety, right? And then I have actually infinitely many such polynomials, because it's not enough just to take these linear equations, but I also need to take every combination of these guys as well. Okay, so that would be the description of the tropicalized variety. So the second purpose would be, you know, as we said, so there are like infinitely many such equations, but in order to compute these tropicalized varieties, I would like to find like a minimal generating set for this variety, and then see whether it's possible to combinatorially define such equations that are enough to generate the solution space. And the third part is going to, you know, if you look at all these linear subspaces and the modulo space of all these linear subspaces, then you have the variety which is called Grassmannian Dn. So we are going to talk about Grassmannian Dn, and also, you know, talk about the tropicalization of this variety. And if you remember from the second lecture, when we talked about the structure theorem, whenever you have a variety and then you tropicalize it, so the corresponding, you know, tropicalization is a polyhedral complex with some super nice properties, right? So it's pure, it's connected in codimension 1, and it's balanced. So these are called like tropical varieties. If your variety has such a polyhedral complex, but is not necessarily like represented as a tropicalized variety. So here we are going to do the same. So we're going to take the tropicalized linear spaces, look at their corresponding polyhedral complex, and see whether we can kind of, describe like an abstract notions of all points. So like in R1, and that they have these combinatorial properties. So we're gonna define like a notion of tropical linear varieties. And let me just repeat this again, like a tropical linear variety would have some nice combinatorial properties, and every tropicalized linear variety is going to be a tropical linear variety, but is not necessarily, the reverse does not necessarily hold. Okay, perfect. And what do we mean by, by looking at combinatorial condition on tropicalized variety? So the thing is that if you look at, look at the combinatorial description of your tropicalized varieties, so then it turns out that these spaces have some nice properties, and actually, so like every linear space has a combinatorial counterpart, which is called like a matroid, and the properties of this matroid, the invariants of these matroids are enough to generalize tropical linear spaces. Okay, so I'm going to define like all these notions, but this is just an overview of what we're gonna see during this talk. Okay, so so let me start by an example to show you like, what sort of properties we are going to see. We are going to describe like about the variety. So here I take like a linear vector subspace as a row space of this matrix. So I have a 3 times 5 matrix, right? So I have 5 vectors, and I generate my linear space. And I also, label my columns like as x1, x2, up to x5. Okay, so that's a full rank matrix, meaning that, the rank is going to be 3, but there are some dependencies among the columns of this matrix, right? So for example, if you look at the column 3 and 4, you see that, so they're equal. So, that's a minimal dependency among them. And if you look at the column 1, 2, 3, so they're also dependent, because, okay, so maybe I just put these equations here, because if I look at the x1, vector 1 plus x3, so that's going to be twice as my second vector, right? And then I also said 3 and 4 are equal. And then similarly, x1 plus x4 is 2 times x2. So these are the minimal dependencies that are called circuits of this matrix and its corresponding matroid. Okay, so now if I want to look at the this vector space or this variety, so that means all the points like in R5 that they satisfy these properties, right? All the points, let's say W in R5, such that these equations hold. So now I want to tropicalize this variety. So the first thing is, you start from these 3 equations, and then you tropicalize each of them. You look at the corresponding variety, you intersect them, and then you also have some other polynomials to consider, right? Probably like infinitely many other polynomials that are combinations of these guys. Okay, so we tropicalize the first one. Let's take the trivial valuation, which takes every coefficient to 0. So then the tropicalization of this guy is going to be x1, tropical sum x2, tropical sum x3, right? And then here, so I have x3 plus x4, and also here x1 plus x2 plus x4. Okay, so that's a tropicalization of each of them. And then I'm looking at their common solutions. So that's my trop L, right? The solution space of these 3 tropical hypersurfaces, and also the intersection of other polynomials here. Okay, so let's see what are the solutions of this variety. So if you look at here, so if you remember what was the definition of the tropical hypersurface. So that was the set of all weight vectors W in R5, such that the minimum here, the minimum of each polynomial, when you evaluate it, the minimum is attained at least twice. So here, if I take W in R5, and I want this minimum to be attained twice, so I should have W3 equal to W4, right? And then here, so I could have, I have 3 terms, so I could have W1 equal to W2, or W1 equal to W3, or W2 equal to W3. And then I look at all these inequalities, linear inequalities, right? So my tropicalization would be the set of all those points that the minimum of these 3 tropical polynomials, when I evaluate it like in W, is achieved at least twice. And it turns out that in this example, so I don't need to take these infinitely many polynomial, and these 3 guys are enough to generate my variety. Okay, so if I wanna, look at the corresponding polyhedral complex, so then I just solve these equations, right? I solve these inequalities. So there are 3 possibilities. W5 is kind of free. So I can choose like W5 to be anything because it doesn't contribute, it doesn't show up like in any of these circuits or dependencies of my matrix, right? So here, so I look at all these 3 possible ways that, that I have to have these conditions to be able to have like my W in the tropicalization. Okay, and then, because W5 is kind of redundant, so I can kind of mod out by W5 and look at this, only these 3 rays here. So I can say my tropicalization modulo, this line coming from W5 is actually just these 3 rays. Okay, so is there any question here about the example? So this just shows like an example of the linear subspace that we wrote, we describe the elements of the linear subspace in terms of some equations, right? Linear equations, we tropicalize them, and then we looked at the corresponding tropicalization. And in this particular example, I just wanted to show you that, even though the tropicalization has been defined as the intersection of V of F for every combination of these polynomials. So like in this example is enough just to take these 3 linear equations, which is quite nice because you have a minimal generating set for your variety. Okay, so if there is no question, maybe I just continue. Okay, so, and then I said, for the linear vector subspace, you might also have like another description of your linear space, and that would be in terms of Plūcker coordinates. And that part I'm going to explain like a little bit because it might not be as common as the first kind of representation of linear spaces. Okay, so to define Plūcker coordinates of the matrix, let's take a matrix like D times n matrix of full rank, which represents a vector space of dimension D in my Kn. Okay, so now I'm going to take like every D subset of 1 to n and look at the corresponding submatrix of A. So I have a D times D submatrix. So I would compute just the determinant of this submatrix, right? And I'm going to call this like the Plūcker coordinates of A indexed by I. Okay, so for every D subset of 1 to n, so I'm going to compute these Plūcker coordinates. And, having all these n choose D subsets and n choose D coordinates, so I'm going to consider like a Plūcker vector, which is just the set of all these guys like as a vector. Maybe you put them like in a lexicographically order. Okay, so that would be the Plūcker vector of my matrix. And maybe we just see an example here. So I have a 2 times 4 matrix, right? That represents like a 2-dimensional vector subspace. And to get to the Plūcker vector, so I'm going to look at the, like the submatrix, like on the first 2 columns, compute this minor, like here is 1, and then I just put it like plug it in like instead of P1, 2. and then I go to P1, 3, plug in the corresponding minor, etc. And then I have 6 such minors. So my Plūcker vector has 6 coordinates. Okay, so on a given, so that, that's like an easy exercise, like in linear algebra, that given such weight vector, you can cook up its corresponding linear space. Okay, so to go to the linear space, so that means I should be able to write the bunch of linear equations that they generate my linear space. Okay, and turns out that you just take these Plūcker coordinates and every d plus 1 subset of 1 to n, and for every such subset, you just write one equation. And the equation is that you take these Plūcker coordinates when you remove the index I, and then instead plug in, the corresponding variable xi. So you have a bunch of these linear equations. At most, n choose d plus 1, and they generate, these linear equations. Somehow, the solution of these linear equations is going to be exactly the same linear space which has given you these Plūcker coordinates. Okay, perfect. So let's look at the example again, like in this 2 times 4 matrix. So what I'm going to do is to take like all these 3 subsets of 1 to 4, and then for each of them, get the corresponding linear equation. So that's it. And then these 4 linear equations are generating the same vector space as my matrix A. Okay, so any question here? Okay, good. So what is yes. So now that we have these Plūcker coordinates, representing these linear vector spaces, we want to parameterize them. And by that, I mean, given a vector in R, n choose D. So I want to look at I want to check whether this given vector is actually coming from a linear space, whether it is a Plūcker vector of a linear space. And then to do this, so we're going to go to the projective space, right? So we're going to look at all those, meaning that, I'm going to identify 2 vectors that they are just the multiplication of each other, okay? And then I'm going to say that, this vector is the Plūcker vector of the matrix, if and only if it satisfies into some quadratic Plūcker relations. So there are a bunch of quadratic degree 2 Plūcker relations that you can write, and then your vector is going to represent like a linear vector subspace if whenever you plug it in here, so like into these Plūcker relations, you always get a 0. And then these Plūcker relations are actually easy to compute. So there's some nice combinatorial way to write them down, but you can also compute them like in, maybe like in Macaulay too. So you just plug in Grassmannian dn, and then it would give you like all the Plūcker relations for such Plūcker vectors. Okay, perfect. So now, if you have, for example, if you have a 2 times 4 matrix as before, so you have only one Plūcker relation, and that's the 3 terms quadratic polynomials that I have written here, P1, 2, P3, 4 minus 1, 3, 2, 4 plus 2, 3, 1, 4. And your vector is going to be, like a vector of a 2-dimensional linear space, like in R4, if and only if it satisfies this one equation. Okay, and it's also easy to see that, these, once you have your linear space, of course, you have different ways, to write down like a matrix representing your space, right? Every matrix and with matrix operations, so you get like another matrix which corresponds to the same linear space, and then both of them, these Plūcker coordinates are going to be like similar, the same like in this projective space. So kind of it's it represents the same linear space. Okay, and so now in order to define the tropical linear spaces, I'm going to look at the tropical projective space, which is the same as before, right? So this time I will choose like this tropical number and then n choose D, and then I would remove, instead of 0, so I would remove the additive identity, like in the tropical world, that would be infinitely infinity. And then I would define like a, like an equivalence relation that two vectors are identified if they are multiplication of each other, like a tropical multiplication, right? And, I said that if you have a vector, so you can write down, like this is like in the real world, right? So not in the tropical world. So if you have a vector, Plūcker vector P, so you can write down all these equations that they're defining your linear space. You write them down here. And then the question is, how do I tropicalize this variety? Yeah, so I have to look at all possible combination of this polynomial to generate my tropical variety. But the easiest, but instead of looking at this variety, so I'm going to take like a larger variety or pre-variety, which is defined by tropicalization of only these linear equations here. Okay, so I think there's a question. Let me double check. So, okay, I cannot see it. Would you like to?
Sean asked, what was alpha I in the previous slide?
In the previous slide. Oh, by alpha I, okay, no, I haven't told you, but okay, so what is it? So you start from, you take a D+1 subset, you remove I, and this is like an ordered set, right? But then you look at and then you add this I to your S, to the end of your S, for example, that could be 1, 3, and then you add 2, but the index is not ordered like anymore. So you kind of, you order it, you write it down like in an increasing order, and this alpha is just the, the signature of this permutation, taking 1, 3, 2 to 1, 2, 3. Okay, so like combinatorial, you can work this out. What are these numbers? Any other question? Okay, now I see that, huh? Okay, perfect. So let me just leave it here. Okay, good. Yeah, and then I said, okay, so you have a linear vector space, defined by linear equations. In order to define the tropicalization of this variety, I have to tropicalize like every polynomial, which is a combination of these guys. But usually we are going to solve, or we are going to study like an easier problem, which is, that's called like a pre-variety, not variety. That's a pre-variety generated as the intersection of the tropical hypersurfaces of these guys, of these linear equations that you see like from the beginning. Okay, and then I say why it makes sense, why does it make sense to study these pre-varieties? Okay, so that's a question, how to describe these elements of the tropicalization like combinatorially. And it turns out that if you only take this pre-variety, if you only tropicalize these equations and then take their intersection, these are not going to be called tropicalized linear spaces, so they're called tropical linear spaces. And combinatorially, they are super nice because they are corresponding to some, some invariants of matroids. And then I'm going to explain why it means like, how you can read them like in terms of some matroids associated to the matrices. And matroids, of course, are super nice because you already, there's a lot of theory like behind, and there is like this fan structure for the matroids, which is called Bergman fan. And this Bergman fan is going to coincide with this tropical fan that we are interested in to compute. Okay, so that was fast, but I just wanted to give you like an idea why, we are looking at the tropicalization of these particular linear equations. So, okay, so let's have a crash course like in matroid theory just to look at the definition. So once you have a matrix with columns 1 to n, we just saw that, by looking at the rank condition, like on the columns of your matrix, you can find what are the dependencies like among the columns, and then what are the minimal dependencies that are called circuits of the matrix. Okay, so these matrices are going to be special case of matroids. They're called linear matroids. Okay, so, but then you have like a more general theory that how would you define like a matroid in general? So similar to this case that you had, n columns, and then you had like these linear equations among these n columns. Here you can say like a matroid on a ground set 1 to n is a collection of circuits, and circuits are just subsets of 1 to n with these properties, with these three properties. First of all, the empty set, we're not going to consider this like a circuit, okay? And these circuits are going to be taking as minimal dependencies, like in a sense that no circuit contains like in another one. No circuit contains like another circuit. And the third condition is that for every pair of circuits C and C prime, if you take an element like in the intersection, okay, so you can remove that element, take the union of these circuits, remove that common element, and then this guy should also contain a circuit. Okay, so the first two are easy, but for the third one is also kind of easy to imagine what's going on, because if, like in terms of the matrix, let's say C and C prime are two circuits of my matrix, right? So that means there is a linear equation. There is a linear equation among those columns, right? And my column A can be written in terms of the other columns like in C, okay? And also my column A can be written in terms of the other columns like in C prime. So now I have two linear equations that they have this A column like in common. So I can just, put this equation to be equal and remove A. So this A will be canceled, and you somehow like find a new dependencies, right? And these dependencies could be minimal, so then you already have a circuit, or it could be non-minimal, so then your circuit contains like another circuit. This union contains like a circuit. Okay, is it clear? Or please let me know if you want more, more example. So this was the matroid, like definition of abstract matroid. And okay, and similarly, as we had basis elements of the matrix, which were, the maximal independent sets, the maximal collection of, independent columns. So here you can also define the maximal independent set that, those collection of those subsets of 1 to n that doesn't contain like any circuit. So it doesn't contain like any dependencies. And for every such elements, for every such dependent set, which is called like a basis, you can define like a 1, 0 vector, which is just the, if your basis is, for example, 1, 2, 3, so we are going to look at the 1, 0 vector, which is 1, 1, 1, and then 0, 0, 0. Okay, you take, for every basis, you take 1, 1, 0 vector, and then you consider the convex hull of these guys, and then what you get is called like a matroid polytope, which has a lot of nice properties. And actually, to define matroids, there are different 15 or 50 different equivalent definitions, and one equivalent definition would be actually in terms of matroid polytopes. What do I mean by that is that a 0, 1 polytope, every polytope whose vertices are just 0, 1 vectors, every such polytope is a matroid polytope, comes from a matroid if and only if whenever you look at the edges of your polytope, you just see EI minus EJ. So that means if you look at the subtraction of one vertex with another one, so you just get like a vector, which is 1, 0, 0, 1, 0, 0, minus 1. And that's it. Okay, so you can take this as a definition of the matroid. Okay, so that was a matroid polytope. And
excuse me,
yes,
Fatemeh, can you just say again can you explain what EB1 is again, the 0, 1 vectors?
Oh, sorry, these are, so this B1 to BR is a basis of my matroid. So that's a subset of 1 to n. Okay, and for every bi, I'm going to take what are these called, like basis vectors, that this is just one like in b1 and then 0 everywhere else.
What's the length? How many entries does EB1 have?
Or just n entries, so there are n vectors, basis elements like in R.
Perfect. Okay, great.
Just one in the entry b1 and 0 everywhere else. So I'm going to show you like 2 examples. Okay, so here is my example. Let's take the 4 vectors, so they're representing a matrix, and this comes with a matroid, right? So you look at these 4 vectors. So then I have a matroid on ground set 1, 2, 3, 4. Okay, so now I have to tell you what are the circuits of my matroid and what are the independent set bases and what is the matroid polytope. Okay, so let's check this example together. So this is my matrix representing like a matroid. So all I need to do is to look at the rank function, right? So like, for example, my vector 1 and 2 are independent, right? 1 and 3 are independent, 2 and 4 are independent, but 3 and 4 are not independent. So that means the union of 3 and 4 is a circuit, is a minimal dependency. Okay, so here, so the circuits of corresponding associated matroid is going to be this set 3, 4. Okay, and then I don't have like any other circuit of size 2. So then I look at the circuits of size 3. So then every 3 subset is dependent, right? Because I'm in R2. So these are the vectors in R2. So for example, 1, 2, 4 is dependent. So 1, 2, 3 is dependent. And also 1, 3, 4 is dependent set, right? But because it contains a circuit, so I don't count it like as a circuit. So somehow like the minimal dependencies are going to be only 3, 4, 1, 2, 4, 1, 2, 3. Is it clear? Okay, so these are the circuits, minimal dependencies. And then I can also look at the, maximal independent sets, maximal independent vector. And they're going to be, this is like a, matrix of rank 2. So this A is a matrix of rank 2. So like every pair of vectors are going to be independent except these 3 and 4. Okay, so that's why I have 1, 2, 1, 3, 1, 4, 2, 3, 2, 4 as independent sets. And then to get to the polytope, so I take every basis element and then I associate like a 1, 0 vector of length 4. Okay, so this 1, 2 would be corresponding to the vector 1, 1, 0, 0, because I have 1 and 2, right? And then 1, 3 would be 1, 0, 1, etc. And then 2, 4 would be 0, 1, 0, 1. Okay, so these are the points like in Rn representing my maximal independent sets. So I have 5 such points, and then I consider their convex hull. So I have a square here, and I have a point, and then I take the, the convex hull, that would be the matroid polytope. Okay, good. And then I have, let me show you like another example, which is even more important because that's called uniform matroid, uniform matroid Ud.n, which somehow like shows up like when I want to define my linear vector spaces. So to define this uniform matroid, I'm going to take the circuits to be all D+1 subsets of 1 to n. So for example, the circuits of U24 are going to be all 3 subsets, and the independent sets are going to be all 2 subsets of 1 to 4. And and the corresponding matroid polytope, which is somehow like the convex hull of all 1, 0 vectors that they have exactly D1 and then n minus D zeros. Right, so I plug in these points and then I take the convex hull. That would be my matroid polytope, which is called the hypersimplex. And this hypersimplex shows up in various contexts. Okay, and that's the second example. And now let's go back to the tropical linear subspace. So I said, if you have a linear subspace, somehow like, you take the representation by a matrix, so that already comes with an associated matroid. And then, this matroid has a polytope attached to it. And we're going to say a matroid is loopless if every element is in some basis of M. So another thing that I have to repeat is that, what was the definition of matroid polytope was that it was the convex hull of all these basis elements. And then it had this property that whenever you look at the edges of your matroid polytope, so they are just EI minus EJ for some IJ. Okay, so that means, so that was a characterization for matroid polytope. So every face of matroid polytope is going to be also like a matroid polytope. For example, okay, so I have it like here. Okay, so here, is the matroid that we just saw with 5 independent sets. And then if I look at this face, this facet, like triangle drawn like in brown, so I see that the vertices are 1, 2, 1, 3, 1, 4, and they also represent like a matroid, which is smaller than the original one. Okay, because if you take the matroid polytope as a definition of the matroid. Okay, so and then I'm going to say like a matroid is loopless if every element of 1 to n is in some basis of my matroid. For example, if I take my ground set to be 1 to 4, so this brown face is a loopless matroid, representing like a loopless matroid. But then if I take, okay, so this, this green facet, which is large, like in the back, it has independent sets 1, 2, 1, 4, 2, 4. So they are the subsets of 1 to 4. So 3 is missing here. So 3 is a loop. And this is somehow, this is still like a matroid, but not a loopless one. Okay, so I take like my matroid polytope, I detect which faces are representing loopless matroids. Like here would be this, the brown facet here, and also this is square. This is square, and also the small one here, 1, 2, 2, 3, 2, 4. So I mark these 3 guys, and I look at its corresponding dual fan. So that means these rays that they are dual, to these hyperplanes defining my defining the corresponding polytope, the corresponding facet of my polytope. So then the theorem is that this dual polyhedral fan that you draw here is actually the tropicalization of my linear space L. Okay, so let me repeat this theorem. So you saw from a linear subspace, it has been defined by a bunch of linear equations. You tropicalize those linear equations, you intersect their corresponding hypersurfaces. Okay, so that's called tropical linear subspace. And every tropical linear subspace, has a nice polyhedral complex, right? Which was pure balance connected in codimension 1. That complex is exactly the normal fan of this, of the loopless faces of this matroid. Okay, I see there is a question. No? So is there any question? Or we are good? Okay, so that was kind of like a nice, nice characterization for these linear spaces and their tropicalization, right? The pre-variety of the tropicalization. So, okay, and then, just to compare it with what we saw before. So this is exactly the same example that I had in the beginning, that I had a matrix 3 times 5 matrix, and the kind of the vector 5 was independent, was kind of redundant. And then I tropicalized my variety, and I looked at, its corresponding variety, its corresponding picture, and that was just the 3 rays that I saw, right? And they were exactly those that you obtain as a normal fan of this polytope. Okay, so now the next step would be to go to look at the kind of modular space of these linear vector subspaces. So they're called Grassmannian Dn. So that's the set of all d-dimensional subspaces like in Kn. Okay, so every point in Grassmannian represents a linear space, and every point like in Grassmannian, comes with a d times n matrix, which is a full rank. For example, if I'm in Grassmannian 2, 4, so I can find a 2 times 4 matrix, and like how to compute its Plūcker coordinates and Plūcker vectors, etc. So now, okay, and then also we also saw that every such Plūcker vector satisfies a certain collection of quadratic Plūcker forms, like Plūcker relations, and these are exactly the same one as we saw before. So now the question was to tropicalize, like instead of looking at the tropicalization of the linear spaces, I'm going to look at the tropicalization of the whole space containing all those linear spaces. So the question is tropicalizing this Grassmannian, and the point of this tropical Grassmannian are exactly these tropicalized linear spaces. Okay, so let me again recall, what was a tropicalization of a variety. Like in this particular example, the point in the Grassmannian, so the points of my variety are Plūcker vectors, and I'm going to tropicalize these Plūcker vectors. Okay, so one way to do this, like in this specific case that you have a nice representation of the matrix, and then every matrix represents like a Plūcker vector. So you can actually define this Plūcker, you can see this tropicalized Plūcker vector directly from the matrix. So the way to see this is you take, you have a d times n matrix with entries like in R bar. And again, you're gonna take like every d subset. And instead of looking at this time, like instead of defining these Plūcker coordinates to be the determinant of the corresponding submatrix, we're gonna look at the tropicalization of the corresponding submatrix. The corresponding submatrix is a polynomial, right? So this is like a polynomial, and we just tropicalize it, meaning that we, we change like the plus to tropical sum, which is going to be taking minimum like among bunch of linear forms, and also the multiplication to plus. Okay, so, and then you can define like the tropical Plūcker coordinates, and the same way, instead of Plūcker vector, now you have the tropicalized Plūcker vector, that they are just a bunch of, there's a vector whose entries are going to be these tropical Plūcker coordinates. Okay, so these are the objects that we are interested to compute. But actually the computation of these tropicalized Grassmannian and the tropicalized Plūcker vectors are not easy. So they're only done for Grassmannian 2n, Grassmannian 3.6, 3.7, and even Grassmannian 3.8 is not complete. So there are lots of there are a lot of like active researchers working like in this area, but it's not really easy computationally to find, even to verify points like in the tropicalization of Grassmannians. Okay, but what is important is that, what we saw before is that if you start from a linear vector space and you look at the tropical linear subspaces, so then they are corresponding to Matroid polytopes and, the dual fan of some specific faces of this polytope, right? So another question is whether there is a combinatorial way to kind of, detect these tropicalized Plūcker vectors, whether I can combinatorially somehow like see these vectors, right? And it turns out that these are actually, the tropical linear spaces, the point in the tropical Grassmannian are corresponding to Matroid polytopes, and also tropical Plūcker vectors, what we define here, are corresponding to subdivisions of this, the hypersimplex. That was the Matroid polytope of the uniform polytope Ud.n. Okay, so let me now explain what I mean by this last, 2 sentences here. So, okay. So we're going to define like a tropical Plūcker vector. So that's the definition that we're going to use. a Plūcker a vector P, like in R bar and choose D, is going to be called tropical Plūcker vector. If you know, you start from the matroid polytope of the uniform matroid, which was defined as the convex hull of all these subsets of 1 to n. So that's my hypersimplex. You start from this polytope and you use these vectors to lift the vertices of your polytope 1 dimension higher. Okay, and this, you know, this lifting would induce like a regular subdivision on your original polytope. And then if you look at this regular subdivision and see that every cell of this regular subdivision is itself a matroid polytope, so then this vector is going to be called tropical Plūcker vector. Okay, so I know there are too many definitions here, but I'm going to explain these words like in the next slides. Okay, just to recall what we said. So that was, you know, the hypersimplex delta 2n, 2, 4, right? Because I have taken like all two subsets of 1, 2, 4. So like 1, 2, 1, 3, 1, 4, etc. So I have taken the convex hull of their corresponding 0, 1 vector. Okay, so that's my hypersimplex. And I'm going to you know, to look at different subdivisions of this polytope. So different ways that I can subdivide this polytope to, you know, finitely many polytopes like this one. You know, I have kind of subdivided it like in the square. So I have two smaller polytope. And then if you see, each of them are actually matroid polytopes. So the first one was a matroid polytope you know, that had only one circuit of size 2, namely 3, 4, and the other one is also similar. So the one I think with, or maybe my labeling actually is not good. So 3, 4 should be here, and also 1, 2 should be here. Okay, so I'm going to subdivide. So this subdivision, this picture should show you like a subdivision of the hypersimplex to two smaller polytopes that each of them are indeed matroid polytopes. And if this subdivision has been induced by a vector, like as a regular subdivision, so then that vector is going to be called tropical Plūcker vector. Okay, so let me remind you again what is regular subdivision. Is there like any question here, or shall I go on?
Fatemeh, I'm kind of confused about how you're supposed to check whether a particular complex is a matroid, comes from a matroid or not. I mean, is there a simple way to check that, or do you just have to check all the sets?
Yes, that's a very good question. So the definition of the matroid polytope is that, you know, I look at the edges of my polytope, okay, and then the difference of their corresponding vectors. So this is the vertex 1, 2. So by that, I mean, you know, I have a 4 vector here, which is 1, 1, 0, 0. And I have a 4 vector here, which is 1, 0, 1, 0. Okay. And this edge has been represented, you know, you have two vectors, you want to look at the edge between them. So you have to look at the difference of these two vectors, right? And that, if you look at the difference, so that's going to be 0. Difference of 1, 2 minus 1, 3 is going to be 0, coming from 1 minus 1. And then 1 coming from 2, because you have 2 here, you don't have 2 here, 0, 1. And then minus 1 coming from this 3. And then again, for 4, you have 0. And then if, you know, this edge is bunch of 0 and just 1, 1, and then 1 minus 1. So if this is true for every edge of your polytope, so that's going to be your matroid polytope.
Thank you.
Okay, so that's the if and only if condition. You just look at the edges of your polytope and then the difference between their vectors, and then you see whether this vector is like 1, minus 1, and 0, 0. And of course, if you start from a matroid polytope, okay, so then every existing edge of this polytope has this property, right? So if I subdivide my polytope in a way that, you know, these edges are the previous edges or the original edges, I haven't created like any new edges. So these are going to satisfy this property. So they're indeed Matroid polytope. So like in this specific cases, so I haven't created like any new edge. Okay, but if I would, for example, subdivide it like here, so then I would create like a new edge, which was, you know, between 1, 3, and 2, 4. So then I had to double check whether 1, 3 minus 2, 4 is of form 1 minus 1, 0, which is not the case because the differences, you know, are in 2 entries. So it's not going to be the Matroid polytope. Okay, so the next step, so I'm going to recall what is the regular subdivision, right? Because they're not just usual subdivisions. I have to only check regular subdivisions induced by these vectors. Okay, so think of it like algorithmically that you are giving me like a point, like in n choose d, and you're asking me whether this point is in the tropical of my linear space. I take your point and I use this to lift every vertex of my hypersimplex to 1 dimension higher. Okay, and then I subdivide, and then I project it back to the original space. And if I see a subdivision of this hypersimplex into Matroid polytopes, so then the answer is yes, this is like a tropical Plūcker vector. Otherwise, the answer is no. So, okay, let me recall what was the subdivision of polytope. So this is, I think, what we've seen like in the first lecture. So as subdivision, you know, here I have a pentagon, I have a polytope, and I'm interested in, you know, all subdivisions, all different ways that I can subdivide the polytope. Okay, so there are 5 different ways that I can triangulate this pentagon. So they're the maximal subdivisions, right? I have drawn them all here. And of course, you know, there are some subdivisions that are not maximal, meaning that here I have like a triangle and I have a square, right? And it turns out that if you draw like all your subdivision like in a way that, you know, 2 adjacent, you know, I put them like in an order such that like every 2 adjacent one, I kind of share, you know, at least share some of these edges, right? So the only difference here, for example, to go from here to here is you fix this edge and you just flip one of the edges like in the triangulation to this guy. If you order them nicely, so then they have a fan structure. So meaning that there is a fan, which is called the secondary fan of my polytope. And then, you know, the cones of this fan are corresponding to the maximal subdivisions, are corresponding to my triangulations, and the lower dimensional faces on my cone are corresponding to other subdivisions. For example, here, so the cones are corresponding to triangulations, the rays are corresponding to subdivisions that they have just 1 triangle, 1 square, and then also like in the origin, which is the only vertex. So I have the pentagon, which hasn't been subdivided. Okay, so there is this beautiful theory of secondary fan and secondary polytope that says, you know, if you look at all regular subdivisions of your polytope, so they form a fan, and this fan has some nice properties. Okay, so that was just looking at the subdivisions. And then what is the regular subdivision? You know, we saw this picture like in the first lecture that I had a polytope, which was a Newton polytope of some polynomial with 1, 2, 3, 4, 5, 6 vertices, right? And then I used the coefficients of my polynomial to lift this polynomial to 1 dimension higher. So these 3, you know, vertices of my polytope has been lifted to R3 by adding 1 coordinate 1 to the corresponding vectors, right? For example, this one was 0, 0 in R2, so I went to R3 by adding 0, 0, 1, and so on. Okay, so I go 1 dimension higher. So I consider the convex hull, and you know, I have a polyhedral upstairs, and then I project it back to the original space, to R2, and that would induce like a subdivision here. So like in this case, I have subdivided my original triangle to 4 little triangles. Okay, so that's called regular subdivision. Or maybe to give you like an easier example, here I have a polytope with 2 vertices, and I could also take some vertices like inside my polytope, and I have, and I have kind of, lifted up like every point here, okay, and then I took the lower envelope of these guys, the convex hull of these guys, and I project them back here. And then what I see is that, that induces like a subdivision of my original polytope into 3 little lines, right? So that's a regular subdivision. Okay, and what we saw like as a definition of tropical Plücker vector is that if you take a vector in this space and you use it, to lift up the vertices of this polytope, of this matroid polytope, and you project it back to the original space, and you obtain like a subdivision of this guy. And if every polytope like in the subdivision is again like a matroid polytope, so this point lives like in the tropical vector space. Okay, and what is even more important is that now if you take the polyhedral dual fan of this subdivision, so that's going to be like a tropical linear space. So this fan, the dual fan, has some nice properties again, it's pure, balanced, etc. And that represents like a tropical linear space. Okay, so just to conclude, what we've seen is actually what I defined, or like, originally I was interested like in tropical Grassmannian Dn, which was the tropicalization of all those Plücker vectors and tropicalization of the Grassmannian variety. But what we saw from combinatorial point of view was that, instead of looking at the tropical Grassmannian, we looked at what we call Dressian Dn, and Dressians parameterize abstract tropical linear spaces. So it means parameterize all those nice polyhedral complexes that you could get like as a tropicalization of varieties. And they are the modular space of all those tropical Plücker vectors. Again, tropical Plücker vectors were corresponding to these subdivisions of the hypersimplex, right, of this polytope of the uniform matroid. And we saw that, this has a nice natural fan structure. Namely, you can look at the secondary fan of this matroid polytope, right? And among these secondary fans, so they're all induced by, by some weights, right? By some vectors. So they're all polytopes or subdivisions like in the secondary fan has been obtained by lifting your polytope upstairs and then projecting it back. Okay, but then here you do this, but then you look at just the subfan of the secondary fan, namely those guys that they are when you have the subdivision, so they're all going to be matroid subdivisions. And this subfan is called like this Dressian, which is the kind of parameterization of these tropical linear spaces. Okay, so how about these tropical Grassmannians that we were interested in? So they have been studied a lot. So they are, again, tropicalization varieties that you can obtain by tropicalizing, all those Plücker relations, quadratic Plücker relations, or you could, by fundamental theorem, you could take all these Plücker vectors and you tropicalize your Plücker vectors. You take the image of the valuation map of those Plücker vectors. And what we saw is that these, every element of the tropical Grassmannian Dn is an element in the Dressian, meaning that, all these nice combinatorial properties that we saw for tropical vectors satisfy for every point of the tropical Grassmannian. Okay, but the inverse might not be true. So the only case that's true is actually tropical Grassmannian 2n, that it's just like the tropicalized line in the tropical projective n-1 dimensional space. And these tropical Grassmannian 2n are particularly nice because they're kind of representing the space of phylogenetic trees with n leaves. So you have, every point in the tropical Grassmannian 2n represents like such a tree, such a metric tree that actually, if you look at the different lengths, different distance between the leaves I and j, so that would tell you what is the coordinate Pij in your Plūcker vector. So here we have the equality, and that's why, everything works super nice, like in the case of Grassmannian 2n. And as I said, these are understanding these tropical Grassmannians, and both from theoretical point of view and computational point of views are very interesting. So they have been studied a lot, and they're computationally heavy and challenging, especially, the easiest examples are tropical Grassmannian 3n, even though they are coming with some nice combinatorial properties. For example, tropical Grassmannian 3n are metric tree arrangement. So here in 2n you have just one tree, in 3n you have n tree arrangement, but still we cannot do the computation. So we cannot find like all points like in the tropicalization, or we cannot describe the fan structure of the tropicalization. And I think the first unknown case is still like Grassmannian 3.8. Okay, perfect. So maybe I just stay here, and then if you have a question, please unmute yourself and go ahead.
Fatemeh, could you go back to the slide with the the pentagons and the fan?
The pentagon, was it here? Yes.
Yes, this one.
Mm-hmm.
I'd like to see the theorem at the bottom. I missed that.
Oh, you mean this one, the secondary fan?
Yes.
Oh, so the theorem says that, if you look at the set of these subdivisions of any polytope, okay, this forms like a fan. So this has a fan structure such that every face of this polyhedral fan represents one regular subdivision of your polytope.
Mm-hmm.
Yes.
And in the next slide, was there a theorem of Kapranov at the bottom? Oh, no.
Oh, yeah, here.
Oh, here it is. Yeah,
yeah,
this is what I missed.
Okay, so what I mean here is that, you start from this Plūcker, tropical Plūcker vector, right? So you subdivide your hypersimplex. So like here, they're divided like in two parts. And then you look at the dual fan of this subdivision. So like here, dual fan, for this part, so the dual fan is just this line that I have drawn before. And then here again, this would be the line, right? Because we know what are the duals of each of them, right? Okay, maybe I go back. Okay, so if I go back here, so I show you like what is the, okay, here, yes, exactly. So here, that's the dual fan of this part. And also for the other polytope was also kind of, the mirror image of this guy, right? So that was the other side, like this one.
Got it.
And they're glued along this edge. So what I would obtain as a polyhedral dual fan would be this guy, would be such a tree. And that's the, the tropicalization of my variety. That's a polyhedral complex that we saw like in the structure theorem.
It seems quite difficult to lift these the vectors in the uniform matroid and compute the lower envelope. That's not obvious to me how you're supposed to do
You mean
that.
computationally how you would do this?
Yeah.
I mean, it's more with practice, like, in the examples, but I think computationally you can do, if I'm not mistaken, like Polymake. Like in Polymake, you should be able to do some of this computation.
I see. Okay, very good.
Yes. So is there any other question?
Hi.
Yes.
I'm wondering if the results for like where the hypersimplex appears, if these results can be generalized to other polytopes.
Yes, this
Because
is
the
a very
hypersimplex corresponds to the uniform matrix, right? So for other matrices, we have other polytopes.
yes. So
And,
this is a very good question, and that's true. Yes. So like every theorem that you saw here has a generalized version in terms of every polytope, right? But here I just chose to talk about the hypersimplex because these hypersimplex, would be corresponding to these tropical Plücker coordinates when none of these coordinates are actually 0. And if some of these coordinates are 0, so that means, okay, so these are going to be 0 if the corresponding subset I, sorry, Pi is 0 if the corresponding subset I is not an independent set, but, it's a circuit like in your Matroid.
And this would correspond to a subset of the Dressian as well.
Yes, exactly.
Okay. Okay.
Yes. So you can define the Dressian. So this Dressian that we saw here is defined for hypersimplex, but the same definition works for every Matroid. You can have, like, instead of writing Dressian dn, you would just write Dressian sub m with the same definitions.